Hey everybody, it's Ripley again. We're going to go over section 7.5 half and double angles. And what I'm going to do is I'm going to give you some formulas that I have to give this as a sort of a cautionary tale. You got to be real careful. You don't have to memorize these. You don't have to commit these to memory if you don't want to, because you're going to have a formula sheet that you get to work from. However, it will behoove you to have some of these memorized, to be able to grab them sort of quickly out of the air. All right, so what we're going to do here is remember, a lot of these formulas were come up with so that people could fill in gaps. All right, we know our pi thirds, we know our pi sixths, we know our pi fourths, our pi halves, etc., etc. But the problem is as I showed you in 7.4, what if I want to deal with pi twelfths, right? What if I want to deal with pi eighths? Remember, I made that promise back in 7.4, and I'll show you how that works here in just a sec. Excuse me. All right, so first things first, what we're going to do is we're going to analyze what it looks like to talk about the cosine of, say, 2 theta, okay? So if I know what theta is for whatever reason, and I want to double it for whatever reason, then is there a nice, pretty formula? Because, I mean, if you think about it, if you're coming up with these sort of mathematics early in the day, you're going to start with real easy things, you know, double angles, half angles, things like that. All right, so check this out. It's a real simple formula. All I'm going to do is I'm going to take the cosine of 2 theta, and I'm going to turn it into the cosine of theta plus theta, because last I checked, theta plus theta is 2 theta. And then I'm going to use my sum and difference formulas from cosine, and if you remember, this is going to be cos theta minus sine theta, okay? So you can tell what this is going to turn into. It's going to turn into cos squared theta minus sine squared theta, all right? But I can also rewrite this if I want to. If you think about it, cos squared is 1 minus sine squared, so I can write this as 1 minus sine squared theta minus sine squared theta, right? Because that's, see what I did? I just turned this guy into this guy, and I end up with 1 minus 2 sine squared theta. Nothing to it. Similarly, let's change colors again. I know I get obnoxious with colors. I just like colors. Leave me alone. I do what I want. Okay, I can also do the same trick with sine squared. So I end up with cos squared theta minus parenthesis 1 minus cos squared theta, because that's what sine squared is, right? I'm just using my Pythagorean identity. And check it out. I end up with cos squared minus 1 minus a negative cos squared. So it ends up being 2 cos squared. Just a simple algebraic process, right? Minus 1. So all three of these guys are cosine of 2 theta. Now you may say, really, why do we need 3 of them? Well, you really don't need 3 of them. You can use 1 of them. But sometimes it's nice, especially if I'm trying to prove identities, it's really nice to be able to use these. Okay? All right, so let's do sine of 2 theta. All right? And we'll think about that, because all of these double angle formulas are real nice to work with, because we just use the formulas. It's easy. Okay, we use the sum and difference formulas. So this is going to be sine theta plus theta, right? Because that's what 2 theta is. And then I go sine theta cos theta plus cos theta sine theta. Well, last time I checked, cos theta sine theta is exactly the same as sine theta cos theta. So if I combine like terms, I get 2 sine theta cos theta. All right, and there's nothing really fancy that you want to do here like we did up here, because these aren't squared terms, so I'm going to end up with square roots, and it's just going to be awful. Okay, similarly, let's do tangent of 2 theta. Well, again, it's just tan of theta plus, stylus is going crazy, sorry about that, which I know that this is tangent of theta plus tangent of theta. Remember, the top was always tan alpha plus tan beta if I'm adding, over 1 minus tan theta, tan theta. I'm just using, you see what we're doing here, guys? We're taking the identities that we've already proven, and we're just building more useful tools. It's tool building in an intellectual and mathematical sense. It really is. You start with something real simple. Hey, let's define x and y as being sine and cos, and let's put it on the unit circle and see what happens. And then we're like, well, we want to fill in some points on the unit circle. So let's do that. You know what I mean? That's kind of an interesting way of thinking about it. We are tool building, that's it. I can just pardon me while I get off of my speech. This ends up being 2 tan theta divided by 1 minus tan squared theta. Just a little algebra there. And it was a piece of cake. Hey, look at that. We got our sines, we got our coses, we got our tangents of double angles. Okay. Now, there's something that's referred to as reduction in powers. Reduction in power. And I'll show you this one real quick. And it's very useful. I know for sure that I can write sine squared theta as 1 minus cosine squared. The problem is that's not always useful. So I want to show you another way to write sine squared and cos squared. Okay? Even though this is perfectly logical, perfectly okay, it may not be helpful. I may not be able to use it with certain identities. So let me show you something. It's actually pretty easy to do. Check it out. I know that sine squared theta plus cos squared theta equals 1. It's the Pythagorean identity. And I now know that cos squared theta minus sine squared theta equals the cosine of 2 theta. All right? Now, what I want to do is I want to turn sine squared theta into something that doesn't have a square in it. Okay, I'm going to try and get rid of that square. All right, but I'm not allowed to just take the square root, right? That would be illegal, mathematically speaking. So watch this. Well, look at here. What if I were to subtract the bottom equation from the top equation? What would happen? Well, negative cos squared, right? That would cancel with that because this would be a negative, right? I could turn this into a plus and then just fill in with a negative there and a positive there, right? I just distributed the negative through. Don't forget your negative over here as well, right? Because I got it. What I do to one side of the equation, I got to do to the other. So the cosine squareds would cancel, and I'd end up with 2 sine squared theta equals 1 minus cos 2 theta, right? Now just divide through. So look at what I have now. I've got 1 minus cos 2 theta. Remember, this 2 theta is actually the angle measure. We got to respect that fact. It's not the cosine of 2. You know, radian measure 2 times some theta value, so times some variable, and then divide by 2. Check it out. I had a squared. Now I have nothing in terms of squares. Similarly, if I do exactly the same thing, if I look at sine squared, plus cos squared, there should be a theta there, right? Equals 1, and cos squared minus sine squared equals cos 2 theta, and I add them, what happens? Well, now my sines cancel. If I add them, and I end up with 2 cos squared theta equals 1 plus cos 2 theta. If I divide through by 2, I get cos squared theta equals 1 plus cos 2 theta over 2. And again, I've reduced the formulas. See, all that I'm doing is just a logical two-step. Again, you can always write cos squared as 1 minus sine squared. You can always write sine squared as 1 minus cos squared, but sometimes it's more helpful to have it in this form. It's easier to play with, okay? All right, so that takes care of half and double angles and reduction in power. Now let's talk about did I say half and double? I'm sorry, double angles and reduction in power. Now I want to talk about half angles.